So this is our continuation of Newton's laws note. So we're going to look at practice question number 2 for Newton's second law. Okay, so in this one we have a cyclist who is increasing velocity from 6 meters per second going to the east to 14 meters per second going to the east in 6 seconds. The total mass of the cyclist and the bike is 58 kilograms. Find the net force acting on the cyclist and the bicycle. Okay, so in this question, we're not quite given the acceleration, but we are given enough information to find it. So we know we're going from 6 meters per second to 14 meters per second, and we know that's happening in 6 seconds. So we can calculate our acceleration by using our kinematic equation, Vf minus Vi over the change in time. So our Vf is 14 meters per second, and our Vi was 6 meters per second, and then our time was 6 seconds. So overall, we're accelerating at 1.33 meters per second squared, and that's still going to the east because both velocities were going to the east. So then if we want to calculate our net force, it's going to be our mass times our acceleration. So the mass of our whole system is 58 kilograms, and our acceleration was what we calculated, 1.33. So our overall net force is going to be 77 newtons, and we're going to be traveling to the east since we've been traveling to the east throughout the question. Okay, so that's Newton's second law. So if Newton's first law does not apply, remember Newton's first law is for an object that's at rest or that is moving at a constant velocity. Then we use Newton's second law. Newton's second law is for an object that's accelerating or decelerating or changing its direction. All right, so let's talk about Newton's third law. So this is the last one. So Newton's third law says that for every force, there is a reactive force that is equal in magnitude and remember magnitude means amount and opposite in direction. So what this means is that whenever we have two objects that are going to come into contact with each other, one object is going to push on the other, and they're going to push back and forth with forces that are equal to each other in magnitude, but that are opposite in direction. Okay, so for example, if we have, say, a car. Okay, so someone traveling in our little car here, and they're going to run into a ball that someone has left on the road. So maybe like a little basketball here. Looks maybe more like a baseball, but okay. So when the car runs into the baseball and they're actually coming into contact with each other, the car is going to have a force on the ball. So this is the force of the car on the ball. But then the ball is going to have a reactive force that pushes back on the car. So this is the force of the ball on the car. And those two forces should be equal to each other in magnitude, but opposite in direction. Okay, we're not going to use this a lot, but we do use it when things are coming into contact with each other. So say we have two boxes that are in contact, and this one is M1 and M2, and they're different sizes, but they're each going to have a force acting on each other. So M1 will have a force acting on M2. M2 will have a force that pushes back on M1. So this would be the force of M1 on M2. And then the equal but opposite direction, we have the force of M2 on M1. Okay, this is really only going to apply when we have two objects that are really coming into contact with each other. Okay, so mainly in this course, we're going to be looking at using Newton's first law or using Newton's second law. So those are the two that we're going to use most often. All right, and that's it. That's the note for Newton's laws.